Hello, college algebra students. You should have 5.3 logarithmic functions and graphs notes that I handed out last week, but I'm also going to send it with an attachment so in case you don't have it. But just like in class, follow along with the notes, take notes. I'm going to be answering the questions on there, and we'll go from there. You also have homework on 5.2, which we covered last week, and 5.3, which I'll be covering today. I suggest you'll be done with all of the lessons for the week. So see if you can do the homework and quiz by Wednesday. You know, free up your holiday and your weekend. But that's just a suggestion. Of course, it's due on Sunday and of this week. So as long as you have it done by then. But see if you can push a little bit to get a little ahead on that. Now we're going to go ahead and jump into it. Here it says we're going to graph x equals 2 to the y. Last week we did exponential functions, so we actually graphed things like y equals 2 to the x, which is very similar except the x and y is interchanged, which in the previous section was what we called inverse functions. So we're actually graphing the inverse function of an exponential, in particular the exponential y equals 2 to the x. So how do I graph anything? We input values. But in this case, we're going to want to input y's, because y is up there in the exponential. So I'm going to use my go-to points, -2, -1, 0, 1, and 2, and we'll just substitute them in for y. 2 to the -1, 2 to the 0, 2 to the 1, 2 to the 2. So we'll start with 2 to the -2. With my negative exponents properties, I know that 2 to the -2 is actually 1 over 2 squared, and 1 over 2 squared is just 1 over 4. And 2 to the -1 is actually 1 over 2 to the first, or just 1/2. Anything to the 0 power is always 1. 2 to the first is 2. 2 squared is 4. So then now all I want to do is just graph this, and we just got to be careful that this is the x, so we're going to graph the x's that way, and then this is the y column. So on the x column, I'm going to go up to 4, because that's what these numbers go up to, and over here on my y's, I'm going to go to -2 and +2. Okay, so now we're going to graph it 1/4 to the right, down 2. 1/2 to the right, down 1. 1 to the right, down 0. 2 to the right, up 1. And then 4 to the right, up 2. So I get this graph of x equals 2 to the y. Now, last week, we graphed things like y equals 2 to the x. So I'm going to do that real quick. 2 to the 0 is 1. 2 to the 1 is 2. 2 to the -1 is 1/2. And 2 to the -2 is 1/4. So if you recall, we did a bunch of graphs that look like that in green. So in green, this is y equals 2 to the x. In red, we graphed its inverse, x equals 2 to the y, which also is known as log base 2 of x. Okay, so that's in fact the inverse. This is what we call the logarithm function is the inverse of the exponential function. So that's what we'll be talking about. And again, you'll see their inverses. If I drew the y equals x, you'll see that the reflections across y equals x, similar to what we did last week. Now, we're going to talk a little bit about how to evaluate logarithms such as this. So a logarithm basically reads log base 10 of 10,000. So what it means is 10 to what exponent will give you 10,000? Well, there's 1, 2, 3, 4 zeros here. So 10 to the 4th power is going to give me 10,000. But sometimes we break it down a little bit more just by simply writing a common base. So this would be 10 to the 4th, And then it makes it very clear. 10 to what power will give you 10,000? Well, 4. Okay. Now here's another log base 10. But again, the goal is the same. 10 to what power will give us 0.01. Now, do you know how to read this? Do you remember back in elementary school that they would tell you this is tenths, hundredth, this is 1/100th. So it might be a bit more beneficial to read it that way, but then also to write it that way. So 0.01 is actually 1/100th, which means log a base 10 of 10 to the -2 by our negative exponent rules, which means as well that 10 to what exponent will give us 0.01, or 10 to what exponent will give us 1/100th. What's now it's a little clearer. It's -2. Okay, so that's how you'd answer this one. And any time you have like a 0.01, you could also think as well the decimal's moving over 2 spaces to the left from this side. Here, log base 2 of 8. We're looking for the exponent of 2. That's going to give us 8. So a quick calculation tells us 2 times 2 is 4, times 2 is 8. That's going to be 3 2's. So the answer is 2, but again, you might do the common base method, and then it becomes very clear. 2 to what power gives you 8? It's 3. Okay. Now, this one's kind of different from the other ones, because here we're going to have to think a little bit more about the exponent, but we're still going to answer the same question. 9 to what power will give us 3? Now, I can think of another relation. I know that the square root of 9 gives us 3, right? And I know that the square root of 9 can be written as to the 1/2 power. 9 to the first power second root. That's the square root of 9. That's anytime you see something to the 1/2 power, that's the square root. And so what that means is if I ask the question, 9 to what power? Well, maybe I shouldn't write it that way. In fact, I probably should just go straight to the answer on this one. But 9 to what power will give me 3? What's 9 to the square root power? Which the square root power is just half. Okay. So that's going to be the power of 9 to the 1/2. And you could always check it, right? But 9 to the 1/2 is actually the square root of 9, which is 3. So we answered the question. 9 to what power will give us 3? It's 1/2 power. Okay. So here's also another one that might come up, but log base 6 of 1. Well, now we got to think, well, what power of 6 will give us 1? Well, these actually turn out to be maybe at first a little tough, but after that, anytime you see log base whatever of 1, well, there's only one exponent that'll give us 1. And so the exponent would be 0, because anything to the 0 power is always 1. So that's, and you could also do this as a change of base, but really it's not necessary. You just answered the question. 6 to what exponent will give you 1? 6 is 0. Okay. And here, you'll see, this is another type, you'll see that they match. Log base 8 of 8. So 8 to what power gives you 8? Well, that one's kind of straightforward. It's going to be 1. Okay, so that's how you can evaluate some logs. Let's talk a little bit about this side we have over here on your worksheet. We're going to do logarithmic form and exponential form. So here you have log base a of x equals y, which is equivalent to x equals a as your base and y as your exponent. So just remember, whatever's on this side, that's your exponent. And then the number here, that's your base. So you'll get some questions. It simply says convert to logarithmic form. Okay, so this is an exponential form. We're going to convert it to logarithmic form. So I already know the base is 2, so I'm going to write log base 2 and of 16, because my exponent is going to be what it equals to. Okay, so it's just a matter of rearranging. Here, you're going to have log base, this is the base, 10 of 0.001 equals the exponent. Okay, so the exponent always is what the log equals to. Here, I have log base e of 70 equals the exponent t. So we've just converted those three into logarithmic form. Now, this asks us to convert to exponential form. Okay, so we're going to do it in reverse. So now it's like we're starting here and we're going back this way. But I'm going to kind of do it a similar way. I can do my base to the exponent. So base to the exponent, I'm going to try and do it this way. But the base to the exponent, 2 to the 5th equals 32. Okay, but I always like to start with the base. Base is a to the exponent is 8, and that's supposed to equal q. Here, log base t is our exponent, or t is our base, x is our exponent, and that's supposed to equal m. Okay, so that's how you convert to exponential functions. Okay, the following examples are just evaluating some logarithms, simply using a calculator. So I showed you how you can evaluate some where they had powers that were convenient. So, and I also told you, well, actually, here's the note that log of x, if there is no base written, it's implied that it's base 10. So again, if there's no base written, it's implied base 10. So right here, there's no base, so it's automatically base 10. If I try to do this in my head, it'd be a little bit difficult because I don't know the power of 10. That's going to give me 645,778. So that's not easily done, but with the calculator, you can just type this in. The log button is right next to the 7 key. And so you can just simply type it exactly as this on a TI-84 or 83 calculator. And same with the next one, you just type it in, you'll get negative 4.62. So try typing this one in and see what you get. So you'll find that the calculator will tell you an error or it can't do it. So why is this? Negatives are not in the domain of logarithms. So that could be a little note for us. Domain of y equals log of x. The domain must be greater than or equal to 0 or 0 to infinity. That's the domain of a logarithm function. So this is not in the domain, therefore it does not exist, or we can just say not in the domain, or does not exist, either one. Okay, so it's, or undefined as well. That'd probably be the best definition of this. But you cannot do it, okay, because it's negative. Okay, so here, I want you to type this in, but you won't be able to type it in just by pushing log, because the log, the only one the calculator does is base 10 by default. So you have to kind of do a different method of doing it. So if you push the button math, which math is right below your green button alpha, okay, on the left side. And if you just push math and then you push up, you'll go to what it says log base. And then if you push log base, it'll allow you to type in 5 and 125. And then you'll see that log base 5 of 125 is 3. Right? And it should be 3 because 5 to what power gives me 125? 5 times 5 is 25. 25 times 5 is 125. So it's 5 to the third power. And here you'll see that if you do log base 2 of 512, I'm going to think about this one. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64, times 2 is 128, times 2 is 256, times 2 is 512. So that's to the 9th power is what I get. Okay, so then if you type this in, go to math, up, and you'll see log base, and then you can type this out, log base 8 of 1 over 64. But I could also do it in another method, but you should try it on the calculator because you're going to need that skill. Which I told you earlier, this could be 1 over 8 squared, which is log base 8 of 8 to the negative 2, so it's negative 2. So that's the exponent of 8. That's going to give you negative 1, or that's going to give me 1 over 64. It's going to be negative 2. Okay, so that's how you do some of these things for logs in a calculator. But now let's talk about natural log. Which the natural log, I have a note here, can be, it's kind of like when you don't write a log, the log is automatically base 10. When you have natural log written as ln, the base is automatically the number e. Which if you remember the number e, it just, if you can just remember the first 2 digits after the decimal, 2.71. Okay, that'll be good enough. So natural log is log base e. Automatic. And other properties are the natural log of 1. In other words, e to what exponent will give you 1? Well, just like any other log of 1 is always 0. Because no matter what the base is, the only exponent that's going to give you 1 is 0. And here's another rule. Natural log of e is 1. Which makes sense because if natural log is a base e, e to what power will give you e? E to the first power. So that's how those rules make sense there. Okay, so we're also going to type these into the calculator, but if you notice the natural log function is right underneath the log. So if you just type in ln 645,778, you should get 13.38. Just make sure you know how to do that. And then for b, natural log of 0.000239, that's should get you negative 10.64. And then for c, if you type in log of negative 5, we'll try it out, see what you get. But then you might be thinking, well, you just told me if I type in a negative, right, what happens? It's undefined. I think your calculator says something like non-real answers, but it's undefined. There's no logs of, you won't get a negative number. Or a negative number shouldn't be in the domain of x, what I wrote there earlier. And you can type in natural log of e, right? But that should just confirm our rule up here. And then you can type in natural log of 1, but e to the 0 power will always give you that. So the last thing to talk about on this part is the change of base formula. Log base b of m equals logs of similar bases. It doesn't matter what base, equals to, or with the m on top and the b and the base here on the bottom. Okay, so again, the a's don't matter. You can pick whatever base. Which it used to be the calculators didn't have that log base function, and all they had was the base 10. So in order to trick the calculator doing questions like this, so if you have a TI-83, you'd have to do this. If you don't have a TI-84, to find answers like this, you would need to change this to log base whatever of 8 over log of 5, and these are equivalent. Now, it's base whatever, so I just left it easy. I don't have to write a base. In fact, this means base 10. Okay, but I could have wrote 3. Okay, but it's common to do that. You could even do, which is equivalent to, and you can try this, natural log of 8 over natural log of 5. You'll get the same exact thing. There's no difference. So that's how you find a solution. And then let's go ahead and calculate it to, let's do natural log of 8 divided by natural log of 5. And I get 1.29. Okay. And yeah, just for kicks, we'll do log of 8 divided by log of 5. But don't take my word for it. You try it. And you should get the same thing. And then if you did the math, log base should be the same thing as well. Okay, so now we're going to graph a little bit more of the logarithms and their inverses on the next section. So we'll start with graphing log of base 10 of x for log of x and y equals 10 of the x. So I'm going to start with the log and make our axes. Well, actually, like anything else, you want to start with your table, and I'm just going to input some values. And I kind of gave you some tips on how we could input values in the last section, but we want to input easy values. Okay, so and this time I don't mean 0, because 0 is not in the domain of this. It has to be greater than 0, like we just said earlier on the note. It has to be from 0 to infinity, but not including 0. Okay, so the next best number would be the number 1. Okay, because I know the log of 1. 10 to what power will give me 1? Well, that's always going to be 0. So anytime you input 1 into a logarithm, you should get, or log of x at least, you should get 0. The next best thing to do would be to input the number that's the base. So in this case, there's no base, but it automatically means base 10. So if I input 10, 10 to what power will give me 10? 1. And you could also do powers of 10, but sometimes that kind of gets outrageous because the next power of 10 would be 100. And I probably don't want to graph that. So 2 points is probably enough to get a good grasp of this. So we're going to we'll graph this. So this is 1, 0, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1. Okay. So 1, 0, 10, 1. And then one thing I haven't talked about here, we did say that the domain is 0 and up, but there's also a vertical asymptote. So there's a vertical asymptote at x equals 0. Okay, and so just with this, I have enough to kind of do a sketch of this graph, which the sketch will look something like that, just off those 2 points. Now, it also says graph y equals 10 to the x, so let me kind of remind you some of the tips that we did last time. Plug in easy points. I won't even make a table. 10 to the 0 is 1. Right? Let me do a different color, though. 10 to the 0 is 1. And 10 to the 1 is 10. So 2, 3, 4, 5, 6, 8, 9, 10. Okay, so, and I could do 10 to the negative 1 is 1/10 and so forth, but I kind of already know that the exponentials have that horizontal asymptote at y equals 0. And then you can clearly see that these are inverses of each other. I can draw that y equals x line, and it shows that there are reflections across that y equals x. So these are the 2 graphs, but really I was kind of focusing on the logarithm graph because that's the one we haven't done quite yet. But let's look at the next one. So we're going to graph natural log of x and e to the x. So first I'm going to make a table and a graph. Okay, so same thing. Natural log, I don't want to plug in 0, right? Because 0 doesn't exist in logarithms. So I'll plug in 1. Because I know the natural log of 1 is the log of 1, which is 0. E to what power gives me 1 is 0. So just remember that rule, that's important. 1's a good number to plug into these. What's another good number to plug into these is their base. This is a natural log, so the base is e. We're just going to plug in e. So natural log of e, by the definition, well, e to what power gives me e is going to be 1. Okay, so now I have 2 points. I have the point 1, 0 and e 1. Well, remember what I said e was. E is 2.71. So we'll put the first point, 2, 0, and then e is about 2.71, 1. And then the knowledge that we have that there's a vertical asymptote at 0 for all logarithms. And there's my graph of my logarithm. And again, we're going to graph the inverse function e to the x, but I'm not going to make a table for that. We'll just kind of do it, plug in some easy points. E to the 0 is 1. E to the 1 is going to be 2.71. And I also know there's a horizontal asymptote at y equals 0, and I have my graph pretty much. And we can see that this is inverse functions. Okay, so they look pretty similar, but slightly different because of the points, but they have that same field sum. But what about ones with different bases? Okay, and maybe some transformations of these. Here we're going to kind of do some of the same principles I said. Just use we'll make a table for the first one, but I don't know about so much for the following ones. But you use some easy numbers. Okay, meaning I can use not 0, okay, don't use 0 for log, right, to substitute for here. So you want 1, because log base 5 of 1, well, the exponent of 5 that gives me 1 is always going to be 0. And then the other tip I gave you was use the base, plug in the base. Because log base 5 of 5, well, 5 to what power gives you 5 is 1. So now I have 2 points, 1, 0, and then 1, 2, 3, 4, 5, 1. Okay, I also know that there's a vertical asymptote here. And there's my graph of log base 5 of x. Okay, now you'll notice that all these other ones are kind of derivations of log base 5 of x. So I'm going to start here. And I want you to think about what transformation is being done from log base 5 of x to arrive to here. Well, log base 5 of x minus 3, that tells me, am I going to shift the graph right, left, up, down? Well, since it's minus 3, I'm going to shift it to the right 3. Okay. Then the plus 6 tells me I'm going to shift it up 6 units. So basically, what I can do is I can just copy my graph up here and do those changes. So 1, 6, 5, 1. Okay, there's my original. But I'm going to transform this to, oh, and can't forget the vertical asymptote. I'm going to transform this to right 3 up 6. So 1, 2, 3, 4, 5, 6. So 1, 2, 3 up 1, 2, 3, 4, 5, 6. There's my new point. And I'm going to do the same here. 1, 2, 3 up 1, 2, 3, 4, 5, 6. There's my new point there. And then I also want to consider that my asymptote is also going to shift right 3. So my asymptote will actually be right here. So now with these 2 points in that asymptote, I have an image. So basically all this did was shift right 3 up 6, and we have our new point. Okay, so let's go with this one here. So what's the transformation being done to log base 5 of x? Well, the negative tells me that's a reflection across y equals 0, or the x-axis, and then the plus 2 tells me I'm going to shift it up 2. So we'll do those one at a time. Okay, so the original would be 1, and then 1, 2, 3, 4, 5, 1. Right, that's this one. If I reflect that, I'm not even going to draw this, I'm just going to reflect it. If I reflect it, it's going to be here with my asymptote this way. So this is the reflection. That's the reflection of this. Now, we'll do the second part of the transformation, which is +2. So we're just going to shift it up 2 units. So up here, same asymptote. There it is. There's my graph. Okay. Now for log base 5 of x minus 3, we have this absolute value, which I don't know if we graphed too many of them, but let's leave that to the end. Let's look at the other parts. I'm going to do x minus 3. So x minus 3, that tells me a right shift of 3. So again, we'll start with the original function. So there's a dot here, and it's 1, 2, 3, 4, 5, up 1. Okay, and I won't even graph it. I'm just going to shift those points right 3. 1, 2, 3. And then 1, 2. Well, I might have trapped myself here because I ran out of space. But there's the right shift. Okay, and then also we'll shift our asymptote. 1, 2, 3. Okay, so here's my graph. Okay, so now to deal with the absolute value part. Now the absolute value is, what does the absolute value do? It makes any number positive, okay? So it's going to make all these values positive, so then I shouldn't have any negative y coordinates. So all that's going to happen is it's going to make these numbers positive, so it's going to make them actually up here. Now these numbers are already positive, therefore they'll stay the same. But that's what the absolute value function of that will look like. Of course, you can graph all these on the calculator just to verify that you're doing it in the right way. Okay. Okay, so in the last section, we're going to continue to graph, but this time there's some natural logarithms, but it also asks you to find the domain of these, so we're going to do that. So here it says natural log of x plus 3, but start with the parent function of this, which we're going to graph the natural log of x. Okay. So if I graph the natural log of x, I can plug in the number 1. Right, so this, again, I'm not going to graph this just yet. I'm going to graph the natural log of x. So plug in 1, you will get 0, right? Because natural log of 1 is 0. Log of 1 of anything is 0, or any base. The base of natural log is e, so I'm going to plug in e. E is 2.71 around here. So natural log of e is going to be 1. So I have somewhat of a graph. Okay, I just need to know that there's a vertical asymptote, and this graph's going to look like this. Okay. So there's my graph of natural log of x. Now, did we graph the one we wanted to? No, but now I can graph that one easily because I know this is going to be a shift to the left because it's plus 3. So I'm going to move these points left 3. 1, 2, 3. 1, 2, 3. Okay, and then also the asymptote. 1, 2, 3. So here is our graph. That's our graph. Natural log of x plus 3. But the question also is asking, find the domain and the vertical asymptote. So we already found the vertical asymptote. So the vertical asymptote is at x equals -3. But the domain, well, we'll use the vertical asymptote because we know that the x is not going to get lower than that. So the domain is -3 to infinity, open, because it won't ever hit -3. So for the next one, it's also natural log of x. So we'll just kind of copy, we already did natural log of x up here. So we'll just kind of copy what we had, which we said that natural log of 1 is 0. It's a good first point. Natural log of e, which is 2.71, is 1. And so there's our natural log function with our asymptote at x equals 0. Now, let's do some of these transformations. One is that it's half. Okay, so we can do that real quick. Half would be here. Half of 0 is 0. So in fact, all the half is going to do is just shrink it by a factor of half. The negative, that'll reflect it across the x-axis. So the reflection of these points in red, well, the reflection of this is just 0. The reflection of this would be half below. So this is the reflection. Okay, so we already did half. That's from black to red, and then we did the reflection. That's the red to the green, and now we're going to do this last shift, which, let's see if I have another color that works. But this one, we're going to shift it up 3. Okay, so 1, 2, 3, and I'm going to shift that point up here. 1, 2, 3. I'm going to shift this point right here up 3. And my asymptote does not change in this case. But there's the graph of this. So it wants the domain and the asymptote. Well, the asymptote is x equals 0. That didn't change here because there's no horizontal shift. And the domain is going to be from 0 to infinity. And again, that didn't change because the asymptote didn't change. So there's our domain. But the other way you can think of it is, if you want the domain inside the logarithm has to be greater than 0, you solve that. There's your domain. Inside this one has to be greater than 0, which is already solved, so it's 0 to infinity. So you can kind of get it without having to draw them, is the point behind that. Now, let's do this last one. And again, we have a natural log function. Let's deal with that at the end, but we want to graph some points. Again, the natural log function is natural log of x, and so we can start there. So natural log of 0 is 1. Natural log of 2 of e is going to be, natural log of 1 is 0, I should say. Natural log of e is 1. E is 2.71, so about right there. So this is ln x, right, the parent function. And now I just want to shift it to the left 1 unit. So let's do that. And I can graph that, but then I also want to shift this vertical asymptote 1 unit. So here's the graph of natural log of x plus 1, but then, okay, now we got to apply the absolute value. So what does the absolute value do? It makes any number positive. So from here on is okay, but we want to make this positive as well. So this will be, if I make this positive, it will just kind of reflect it across the x-axis, and you'll get this, the graph in green. But again, all these you can graph on your calculator. You can verify that these are true. But that'll do it for today. I will see y'all next week, and have a happy Thanksgiving.